Hi everyone, welcome to this particular lecture. In today's lecture, we are going to discuss Gaussian mixture models and how can we use the Gaussian mixture model for generative AI purposes, like for synthetic data generation. Either it is for synthetic stock price generation or implied volatility surface generation, or similar kind of problem statements, right? Uh, Gaussian mixture models are a comparable model and kind of sometimes outperform the modern generative AI models like GAN, that is generative adversarial network, and variational autoencoders. So that's why it becomes very much important for us to discuss GMM, which we call Gaussian mixture models, right? So today we are going to discuss GMM, which is Gaussian mixture models. I think very few know that this can be used for synthetic data generation because uh, I am very much sure that if you have used this particular model, not particularly in quantitative finance, you might have used it for clustering purposes, just like K-means clustering is used. So GMM traditionally has been used for clustering purposes, but like we will try to show that GMM can be also used for synthetic data generation and is simply a generative AI model. So it learns the underlying distribution. It tries to generate similar data, synthetic data for maybe backtesting purposes and all. Okay. So what exactly is a Gaussian mixture model? So I think it's quite clear from the word. If you see the word Gaussian, obviously you will see normal from here, and mixture, obviously you will see multiple mixing of multiple models, right? So the GMM, or which we can say the Gaussian mixture model, is a mixing of multiple normal distribution. Okay, simply, so put simply, GMM is just mixing of multiple normal distributions, right? So before we discuss GMM, I think it's crucial we revise normal distribution, and then we will move back to GMM again. Okay. So what exactly is a normal distribution? Okay. So let us say we have a data set x1, x2, x3, x4, and so on, right? And maybe we plot this data on the x-axis, right? Now the probability density of each of these observations can be written or can be plotted like this, right? If this is the probability density, if this red line is the probability density of the observation, then we say that this observation follows a normal distribution. Okay, so now what is so special about this particular plot, right? If you see the highest, so this is probability density, not the probability. So probability density denotes how much probability is so what is the density of the probability around this particular value. So this has a highest probability density, so means the probability would be higher over there, but it's not exactly the probability. So when you discuss discrete random variable and you see PMF, right, probability mass function, therein if you plot on y-axis, you get exactly the PMF, that is the probability, exact probability. But this value over here, 0.4, is not the probability of 0 over here. Okay, this is the probability density, how much dense the probability is around this particular value. Okay, so this is a very crucial difference, and something that everyone gets confused frequently. Okay, and this is the most asked question as well, because there is a significant difference between PMF and probability density. Okay, so if you see this particular distribution, the highest probability density is toward mean, and as you go away from the mean, the density reduces, right? So this kind of probability, if we have a probability density like this for any certain random variable, we say that this certain random variable follows a normal distribution. Okay, so how to quantify, how to numerically express this plot, right? So the numerical expression for this plot is simply which we write as fx is equal to 1 by root 2 pi sigma square into e to the power minus x minus mu square divided by 2 sigma square. Okay. So this is simply the probability density. So for example, over here, obviously the mu is the mean, which in this case is 0, and sigma is the standard deviation. Okay. Which in this case will probably be 1, a standard deviation. So now if you simply put different x in this particular expression, which is the probability density function, right? This particular expression over here is the probability density function. Okay. So this particular function that you are seeing over here, it gives you the probability density function for any given x. So if you put any other x, right? For example, if you put x equal to -3, mu and sigma are obviously the parameters of the normal distribution. Okay. So mu, which we call mean, and sigma, which we call a standard deviation, are the parameters of the normal distribution. So that's why you will be writing as mu and sigma. Okay. So these are the parameters of a normal distribution. Okay? So if you put any x, it will give you what is the probability density around that particular x. Okay. So that's what fx is all about. Okay. Any doubts so far?
No, I don't have any doubt.
Okay. So let's move ahead. Okay. So let's just advance it a bit, and let's discuss multivariate normal distribution. Okay. So this was a univariate normal distribution. So for example, a stock price, okay, or returns maybe, right? Returns on day 1, returns on day 2, returns on day 3, returns on day 4. A stock price obviously don't follow normal distribution, but just for sake of an example, okay. But returns do follow, that's our assumption in Black-Scholes model. So basically, you can take an example: returns on day 1, returns on day 2, returns on day 3, returns on day 4. They may follow a normal distribution. So this can be an example, right? So this is a kind of univariate normal distribution, right? Now we are going to discuss multivariate normal distribution. Okay. So what is multivariate normal distribution? Uh, So let's first understand through an example. So right now we discuss the returns of any particular stock, right? For example, now what we can do is we can have a matrix X which will be like 2 into 1 matrix. So it will be like R1, which will be return on a stock 1. So let us say IRS1 and RS2. It will be return on a stock 2. Okay. So now X1 we can denote as RS1, RS2. What will be X1? Return on day 1. This particular matrix will contain two returns of two stock 1 and stock 2. Okay. Then x2 will be written on day 2 of the two stocks, right? X3, rs1, rs2. So it denotes the returns on day 3 of two stocks, which are s1 and s2, and so on. So now if I jointly want to understand what is the distribution of x, right? Initially your x was just one value, x1, x2. So now but now your x is a matrix, right? So you will have your own expectation. You will have your own mean for first stock, and you will have another return of another stock, right? So now what we are going to do is, now we are going to write mu as the mean matrix as the mean return of first stock and mean return of second stock. Okay. And now we have two stock. So we won't simply write the variance or a standard deviation, but now we will have something called covariance as well. Okay. So we will have a covariance matrix sigma as well. What will be the size? Size will be 4. So here you will have variance, and here covariance, right? Everyone got it?
Yes.
Okay. So now in case of multivariate normal distribution, we write probability density function. The formula is given by 1 by 2 pi k by 2. What is k by 2? K simply denotes how many dimensional your data is. So here k is 2. Okay. So if you have n rows, you will have n by 2. Okay. Into the determinant, square root of determinant, and then e to the power minus half x minus mu transpose, the variance covariance matrix, and x minus mu. Okay. So what is the size of this X matrix? The size of this X matrix is k rows and one column. So k into 1. What is the size of mu matrix? What is the size of mu matrix? Mu is simply the returns of each stock. So the size will be k into 1 if you have k stock, right? And what is the size of this variance covariance matrix? K into k, right? So this is the expression for probability density function in case you have a multivariate normal distribution. Okay. So now let's go back to the GMM now. Okay. So GMM is all about Gaussian mixture model, is all about mixing of multiple normal distribution. Okay. Mixing of normal distribution. So, okay. So now let us understand it this way. Let's understand it this way. Okay. You have x axis and you have a certain normal distribution. Okay. It will have certain mean. Let us say this mean is, and as of now we have, since the values are on x-axis, let us just assume we have a univariate normal distribution. Okay. So we have mu1 and it's a standard deviation. Let us say it will be sigma 1. Okay. On the same side we can have another normal distribution. Okay. On the x-axis only, which can have another mean and another variance. Let us say it is mu2 and sigma 2. Okay. So now how does mixing happens? Okay. So let's understand it this way. For this so the mixing happens this way. Fx, which is the probability density function fx of mixing, will be W1 into normal distribution of mu1 sigma 1 plus W2 into normal distribution mu2 into sigma 2. Okay. What are W1 and W2? They are weights. Now, what does it mean? Let's understand it very clearly and very simply. So this formula basically tells you, so if you look at this particular formula, this formula out there. So for any given x, let us say this is x1 and this is x1, same thing. So the probability density of x1 according to first normal distribution is something. Okay. Let us say this probability density is 0.3. Okay. And according to this particular normal distribution, let us say the probability density is 0.5. Okay. So what the mixing does is that in the new distribution, whatever will be the new distribution, okay, let us say the new distribution is like this. The probability density of x1 will be, PDF of x1 will be, f of x1 may be 0.3 into w1 plus 0.5 into w2. So for all x on the x-axis, the probability density will now be found out as w1 into what is the probability density according to the first normal distribution plus what is the probability density for that x according to the second normal distribution. Okay. Got it? Did you understand the mixing? How does the mixing happen?
Could you please explain once again?
So what does the mixing does is, we have on x-axis, we have So we have one normal distribution. Let us say this is n1. It is having certain mean and certain standard deviation. Similarly, we have another normal distribution. It is having another mean and another standard deviation. Okay. So now we will now have a mixed distribution. So now we will create a new probability distribution, which will be a mixing of both. So according to the first normal distribution, the probability density for x1 is 0.3, let us say. And according to the second uh, normal distribution, the probability density for x1, the same value is 0.5. So now according to the new probability distribution, the probability density of x1 will be mixing of both. So certain weight into 0.3 plus certain weight into 0.5. Similarly for all x, so for this particular x, what will be uh, PDF? This PDF will be W1 plus whatever is the probability density according to the first distribution plus W2 into whatever is the probability density according to the second distribution. Similarly, for all x, we will be plotting the probability density. Did you get it? So W1 into probability density according to the first distribution plus W2 into probability density for the second distribution. So for all x on the given axis, a new probability density will be generated, which will be based on normal distribution 1 and normal distribution 2. Got it?
Yes, understood. Thank you.
Okay, so now, so these two normal distributions are called component. Okay, we can have multiple component as per our understanding. We can have 10 components, so we'll have 10 distribution, we'll have 10 weights, weight 1 into first distribution, weight 2 into second distribution, weight 3 into third distribution, weight 4 into fourth distribution. Okay, so before we move ahead, let us just go through the I will share my screen, and I will show you how we can get it done using Python. Okay. Is my screen visible?
Yes.
Okay. So first of all, I'm importing libraries. You can see. So now I will be mixing the distribution. So let us see what we are doing. First of all, we are generating points on the x-axis. So we are generating total 1000 points in between -5 to 10. Okay. So now you have to supply. So we are taking two normal distribution right now. First normal distribution is having mean 1 and a standard deviation 1. Second normal distribution is having mean 2 and a standard deviation 2. Okay. And the weights that we are using are W1 and W2. Okay. So now once we have an X, so what this line is doing, this is basically assigning probability density function to all the x-axis according to the first normal distribution. Okay. And similarly, this is assigning the probability density to all value on the x-axis according to the second normal distribution. And finally, we have the mixture. Mixture is W1 into normal 1 plus W2 into normal 2. Okay. So now we will be plotting it. So now let us see what we have done. We are taking the mean of first normal distribution is 2. A standard deviation is 0.5. Mean of second normal distribution is 5 and a standard deviation is 1, and now the mixing ratio is 0.6 and 0.4. So now let us see how does the mixing happen. So see this plot. This line, the blue dotted line, is the first normal distribution, and this orange one is the second normal distribution. Okay. And the one which you see is the black is the mixed normal distribution. So understand it this way. So let us understand through the point 2. So this point 2, which is on the x-axis, is having a probability density of 0.8 according to the first normal distribution. Okay. And around 0 probability density according to the second normal distribution, which is this one. Okay. But if you look at the mixed probability distribution, this point 2 is having certain around 0.5 probability density, right? So this is how mixing happens. So what we are doing is that we are mixing different normal distribution, right? To generate a mixed distribution, mixed model. Okay. So maybe what we can do is we can basically increase the values, and let us see what happens with the plot. So now let us say the mixing is a bit proper, right? So this is the mixing, right? So this is how we mix normal distributions. Okay, so we can mix 10 components, we can mix 15 components as per our wish. So our goal is to ensure that we like so our goal is reverse. Okay, so our goal is not to mix, but our goal is to do something reverse. So I will be telling you what our goal is when we discuss GMM right now. So I hope you at least understand till this portion. If you don't, please ask me out. Otherwise, if you're watching the recording, please comment on the video. No doubt, right?
Notes.
Okay. So let me share my that screen. Okay. So now you understand how this mixing happens, right? So now since you understand how this mixing happens, so what our goal is, that's very much important, specifically for Gaussian mixture model, right? Let us dive into that part. So what I said is that Gaussian mixture takes multiple normal distribution. Okay. Let us say we have k component total, right? So it will assign weights to all those components. So maybe let's write it this way. We have total n components. So k equal to 1 to n. We have total n component. Uh, so the new density, probability density of the uh, x, right, will be based on the weights into the particular normal distribution. So what is the, you know, so now I have written it. So we have total n normal distribution, right? Each normal distribution will be having its own mean and a standard. So what is mu k? Mu k is the mean of kth normal distribution. And similarly, this is the variance covariance matrix of kth normal distribution, right? So what does the Gaussian mixture model do? It combines several normal distribution with its weight to give a new probability density function. Okay, I think that's clear so far. But our goal is different. Our goal is to understand the underlying data. Okay, so what our goal is, particularly if I take a simple example. Okay, so let us say I have a stock price on day 1, stock price on day 2, stock price on day 3, stock price on day 4, stock price on day 5, stock price on day 6, stock price on day 7, stock price on day 8, and so on. Okay, uh, the thing is that obviously this stock price does not follow normal distribution. Okay, right? This stock price does not follow normal distribution. So now what I want to do, I want to test whether this particular distribution or this particular value, is it a sum of, is its probability density function a sum of multiple normal distribution? That can happen, right? So maybe what we are having is that maybe its distribution, its PDF, right, probability density function is a sum of is a mixing of multiple. So these are the observations, right? So now our goal is to understand, is it so? Is it so that this particular, so kind of understand it like this, is this particular value the observed value, this can be any observed value, It can be implied volatility surface, it can be returns, it may be stock price, whatever you say. Okay. Is this particular observation uh, generated from a mixture of multiple normal distribution? Is it so? Okay. If it is, if it is generated from a mixture of multiple normal distribution, then I have several things to answer. Okay. The first thing is how many normal distribution, right? That is the first question. How many normal distributions, right? That is obviously a question that is very much important. So how many components are there? Second thing is, okay, I understand it is generated from n normal distribution or maybe k normal distribution, whatever you say. I understand that. What are the weights of the, what are the weights, corresponding weights, right? That is the second question. What are the weights? Once you answer this question, the question will be asked, what are the weights of all the normal distribution that you have, right? You just say that you have n normal distribution. So what are the weights of these normal distribution, right? What are the mu's and sigmas of this normal distribution? So all the normal distributions will be having mean and variance. So you must answer what are the mean and variance of this normal distribution, right? Okay. So I think we have exactly framed the problem that we want to discuss, right? So now let us see we have solved this particular problem. We have answered these three questions. So what is the profit? The gain is that once you understand that this particular stock price is being generated from these normal distributions with these mean and these variance and these weights, you can simply sample this particular normal distribution multiple times to generate similar data so that you can backtest this multiple times. Okay. So that is the goal. Okay. So once you understand, once you find out from which normal distributions are these values generated, you can simply create synthetic data now. So that is the gain, or that is the reason behind us doing it. Okay. So now we have observed data. Okay. So thing is that what is our goal? Given observed data, given observed data, find the parameters. What are the parameters? Could you please answer? Can anyone say? What are the parameters? One, sir. Okay. So first of all, the first parameter is, so we have observed data, right? So first of all, our goal is number one. So the component part, we decided, in the beginning only. So the number of components that you want to take, the number of normal distributions that you want to take, or maybe you can take, you can repeat this exercise multiple times and choose the one with the, according to the AIC score, right? That is Ekaiki information criterion. Okay. Or PIC, whatever you want to do. So once you decide upon the component, you have to find weights. Second, you have to find mean. And third, you have to find variance, covariance matrix of each of the component normal distribution for each of component normal distribution. Okay, that's the goal. Okay, So while you have Python libraries to do it automatically, I would just, kind of discuss briefly with you how this is done using the popular uh, algorithm, which is the expectation maximization algorithm. I would just discuss it very briefly. You can go through oh, I will explain you how it is done, and a bit of Python code for the univariate case. If you want to derive it, how exactly it's done, I think I will refer you to, I will attach some links to the YouTube video. You can do that. Okay. So our goal is to understand how it is done. So this is done through expectation maximization process. Okay. Expectation maximization process. Or this is, you can also say expectation maximization algorithm. Okay. So expectation maximization algorithm is a powerful method, for finding the maximum likelihood estimates of the parameters, right? So what are the parameters? So what are the maximum likelihood estimates, okay, of the parameters involved? So our goal is to find out these parameters, right? The weights and the means and the variance covariance matrix. So this EM algorithm, right, proceeds of the two step. The first step is the expectation step. Okay. So in the expectation step, what you do is you calculate something called responsibilities. Okay. You calculate something called responsibilities. Let me tell you what these responsibilities are, and it you would obviously understand it in detail, so you don't have to worry about it. Let me just write down the formula. Okay. So first of all, I know it is a bit uh, complex, but it's quite simple. Let me, you know, uh, explain you to quite simple word. So this particular thing is called responsibility. Okay. And what does it mean? What does it mean? So basically, this responsibility describe how responsible is how responsible is kth component. So basically we have k normal distribution, right? So how responsible is the kth? So basically let me write n over here. Okay. N. So we have total n component, right? So how responsible is the kth component of normal distribution for ith observation? Okay. Now, again, you may be confused, Kshitij, what have you written? So let me again simplify it. Okay. So let us say you have observed this particular stock prices. Okay. Univariate case, classic univariate case. So it is very simple. Okay. Again, quite simple. Don't confuse. Okay. So what over here? So you see, let us take only two component. Take only two component, right? Two components. Okay. So what you will be having is S11, S12. Sorry, R11, R12, R21, R22, R31, R32. So understand it this way. We have two components, okay? So this R21 denotes how much, how responsible, or how much responsible, whatever English it is, how much responsible first component is for the observation S2. Similarly, this will denote how responsible, how much the second component is responsible for the observation S3. So for the observation S3, there are two components. Only first one will be responsible and the second one will be responsible. First one and second one. How responsible first one is, this will be R31. How much responsible second one is, it will be R32. If we will have 5 components, then we will have 5 responsible components for each of the observation, right? So we will be calculating the responsibility in the first step. So now in the first step, obviously what we do is we initialize the weights, the mean and the variance randomly first. Okay, using this weight, what we do is we find out what are the responsibilities for each of the observation by each of the component, right? So this is what we do. Okay, so everyone understood this? So how do we do this? How do we do this? So in the bottom, what you have to do is that W1 into normal distribution 1 plus W2 into normal distribution 2 plus W3 into normal distribution 3. If you check the bottom, right? And if you check the numerator, it is just the weight of the kth component, and the normal distribution xi, right? What is the probability density function of xi? So let me show it using the code, and then you will understand it very uh, simply. Okay, okay, so see this one. So here, what we are doing over here is that we are initializing the parameters. So we are initializing mean with 0 and mean 2 with 0, standard deviation with 1, and the weights as 0.5 and 0.5. So we are considering a sample data, a sample observation, which will be one dimensional, of course. Okay, and we are using two components, two normal distribution. So first of all, what we have to do is that we have to find the mean of the both normal distribution, the standard deviation of both the normal distribution, and what are the weights of these normal distribution, right? So we have done this. So now the expectation step, the first step, we have to find the responsibility, right? So as I have already written, to find out the first responsibility 1. So what we have to do is to find out the first responsibility. The first responsibility was, if you remember the formula, normal distribution of x, the probability density of x into weight of 1, okay, divided by the both these ones summation, right? And similarly the res2 will be this value divided by res1 plus res2, right? So this is the responsibility. Okay, so res1 over here, if you remember, check, let me, so what is res1 over there? Okay, if you check res1, what I have written, res1 is weight 1 into normal distribution divided by weight 1 into n1 plus n1 and weight 2 into n2. And similarly res2 will be w1 w2 into n2 and divided by w1 into n1 plus w2 into n2. So the size of res1 will be whatever is the number of observations that you have, right? So for example, if you have p observation, so its size will be p cross 1, right? And similarly it will be have p cross 2. Okay, so this was all about responsibility. Now everything is quite simple. Once you find out the responsibility, the second step is the maximization step, wherein you update the parameters, right? You update the parameters such that the observed value has the maximum probability to happen. Okay, so let me write down the formula. So how do you update your mean? So in the maximization step, you update your mean, you update the variance, you update the weight. Okay. So the means are updated as this. So in our example, how will be the mean updated? Okay. So see, mean. So we have two normal distribution, right? In our example. So the mean one, new mean of will be simply RES1 into, can someone explain me? How will be this be decided? This will be RES1 into XI. Okay. X matrix. Okay. And so it is simply, if I write this way, so this will be simply, you have to multiply the RES matrix with the observation, and in the denominator you have to simply add all the RES1 and RES2. Okay. Sorry, here you have to add RES only, RES1, and simply mu2 new will be RES1 over here, RES2 into XI into summation of RES2. Okay, so let me show it in the code, and then you will get to understand it. So this is where we are updating our uh, means, right? Is my screen being shared?
No, we cannot see the screen.
Okay. Okay, so now it should be visible. So what we have done is that we have updated the mean. So see, how are we updating the mean? Mean one will be updated as the RES1. What does the RES1 matrix contains? First of all, it's very much important for you to understand. The RES1 matrix contains, for each of the observation, what is the responsibility of the first component. Okay, and similarly RES2 tells you for each of the component, right? For each of the observation, what is the responsibility of the second component, right? So we have updated like this, summation of RES1. So this will give you the mean of first observation, mean of the first component and mean of the second component, right? Similarly, this gives you the standard deviation of the first component and a standard deviation of the second component. Similarly, the mixing weight is being given by this. Okay, mixing weight of the first component, mixing weight of the second component will be simply 1 minus W1, right? So let me just run it. Okay, and this is the final one. Okay, so wherein we are doing iterations, so we have to do this step continuously. Find the responsibility, update mean, variance and weight. Find the responsibility, update mean, variance and weight until you reach the convergence. Okay, so here we are taking a sample data, uh, and finally once you take the sample data, so see the sample data we have, which we have taken. So the mean is minus 1 1 uh, for the first component. For the second component, this is this, and these are the weights. Now we will generate our sample data. Okay, this sample data is being generated. Now this sample data will be passed through our EM process. Now what we expect is that this EM process, the parameters that we get, that is the mean of the two components, the standard deviation of the two components and the weights, are closer to this value, because the EM process does not know what are the mean and standard deviation of the sample data that we have passed, right? So let us run it and see whether it happens or not. So see, iteration is being done, and if you check, what are the results, right? What are the results? The mu1 is 0.5 and mu2 is 0.5. Okay, is it so? So this can be done. I think this will have the problem related to the how mean is initialized. So let it be random. Okay, then it will be better. Otherwise, 3, 2. So the mean of first one is 4, and the mean of another one is -1. Is it so? The mean of first one is 4 and the second one is -1. The standard deviation is 1.5 and closer to 1. Again, it is correct. And the weights are 0.7, 0.3. Are the weights so? 0.7, closer to 0.3. So see, though our model didn't know what are the, so what we did, let me repeat it again. We had a sample data. We made it through a mixing of two normal distribution, and we passed the sample data to expectation maximization step of GMM. So the GMM does not know all about it. The GMM only knows that it has two normal distribution. So now what it tries to is that it tries to find out the parameters of the two component normal distribution such that the possibility of finding the observation is maximum. And you see, at last it is able to find out what are the parameters of the normal individual normal distributions, right? And it is closer to what you had. Okay, and if you want to do it for multiple normal distribution, then I have just written this code as well. You can do it using sklearn. So you can just use Gaussian mixture, the number of component, and then the Gaussian mixture dot fit. Okay, so this will help you. So what I have done over here is that if you see, I have generated a normal distribution with this mean. So this is for multivariate. Okay, so I have taken three multivariate normal distribution. Okay, and their means are this 0, 0, 5, 5, and -4, 3. Covariance matrix is this. The weights assigned is 0.3, 0.4, and 0.3. Based on these normal distribution, sorry, based on these weights, we generate a sample. Okay, once we generate this sample, we pass this sample to this particular uh, code. And what this code is does is that, again, EM step, expectation maximization step, to find out the what are the mean, variance, and the weights of the individual normal distribution. Okay, so if I have to repeat what GMM is, now what you will be doing using GMM is, let us say you have a stock price of, let us say, 100 days. What you will be doing is that, first of all, you will be assuming that this stock price is, let us say, generated from 10 normal distribution. Okay, so you will be taking 10 normal distribution. Now you will be trying to find out, okay, I have 10 normal distribution. I am assuming that this particular observation is being generated by a mixing of 10 normal distribution. Now my goal is to find out the weights and the mean and variance of these 10 normal distribution. Once I do it, I can generate as many samples as I want to backtest my data, right? So this is the broad level understanding of GMM that we discussed today. Okay, about the maximize EM step, I think I have just shown you the mixing of the formula for the mixing of two parts, right? I think I will just write down the formula for mixing of other entities involved. Okay, so but you can simply look up at the internet for formula, right? For the maximization. So this is for mean. I, for the sake of completion, I will write it for the variance covariance matrix and the weights as well. So how do you update the variance, right? So this is for mean. You update the variance as summation from I equal to 1 to n. So I don't see any point in writing the formula, but again, for the sake of completion, I'm doing it. In case you want to look at this formula, you can look at it in detail, but probably you want to be using formula again, because you will be using library for this purpose, right? To find out all these parameters. Okay. And finally, the weights, right? So the new weights will be I equal to 1 to n. Sum up all the residuals and the divided by n. Okay, so these will be the new weights for all the k components. So if I had to explain EM step again in brief, what does the EM step contains? First of all, is the ES step where you calculate the responsibility. What are the responsibilities? Responsibility tells you responsibility tells you how much each component of is involved in each of the observation, right? Second step is M step. So using this responsibility, once you calculate the responsibility, you update your weights. Sorry, first of all, you don't update the weight, you update mean. You then update the variance, and then you update the weights. Okay, and then you repeat it multiple times until you reach the convergence. Okay, so probably you will be using libraries for all the purpose, just like I used, though I used the formula for the univariate normal distribution case, but when I sampled three components using multivariate normal distribution, I used library directly. Okay, so I will be sharing the IQINB file directly in the comment. Please go through the YouTube video, understand everything in real. If you have any question, feel free to ask. Okay, and in the next video we'll be seeing a nice use case of GMM. So now, okay, before we move on to the next lecture, you have a task to do. Your task is take any stock price of any stock price, maybe for example for 6 months. Okay, take 6 month data for a stock price. Okay, decide a number of component, decide number of component, right? Once you decide the number of components, then what you have to do is that you have to find the mean, the variance, and the weights of each of the component that gives the maximum probability for the 6 month stock price data. Okay, find mean, variance, and the weights. Okay, so this is your task. Please do this task, share it on X, tag me. I will have a look on your uh, task. Okay, thank you everyone.